Hello. In this video, we'll be looking at the current state of the Cardano peer-to-peer networking. The video consists of two parts. One is a theoretical presentation of the peer-to-peer implementation in Cardano node, and the second part is a practical demonstration of how to use the node in peer-to-peer mode. So, welcome to this theoretical part of the video where we'll be looking at Cardano peer-to-peer networking. And I want to start off with a note saying Cardano peer-to-peer networking is still in development. It has not been officially released. It's not fully feature complete. It's not fully tested, so there might be bugs. And please keep that in mind. And with that, let's get started. Here's an overview of what we'll cover in the presentation. We'll start off with Cardano networking stages, and in this section we'll explain how Cardano networking progressed from the federated network during the Byron era to the current hybrid networking stage, and what peer-to-peer is going to bring to Cardano in the future. We'll then move on to peer-to-peer node components, which are the software components that make peer-to-peer networking possible, and these components are included in the Cardano node. These include peer-to-peer governor, the connection manager, and the server and inbound protocol governor, which we can group into one component for now. We'll move on then to peers and connections, and in this section we'll explore the peer types that exist in Cardano peer-to-peer, as well as the connection types that exist and connection states. Lastly, we'll move on to the node configuration, so the actual configuration files of Cardano node required to run the peer-to-peer mode, as well as the topology file for the peer-to-peer node. Here are brief explanations of each of the mentioned networking stages. So started with the federated one. This is the stage where IOG, core nodes and relays maintain the network completely. All the blocks were minted by IOG nodes, and Cardano apps and wallets connected to the IOG nodes to use the blockchain, specifically their relays, and there were no community stake pools that minted blocks. It was all federated by the IOG nodes. We then progressed to the hybrid stage with the introduction of the Shelley era, in which community stake pools started producing blocks, and currently community stake pools produce all the blocks on the Cardano network. And the way they network between each other is that they connect to a set of peers that they define in the in their static topology files of the nodes. So they can connect both to the IOG relays and the community stake pools. So in this stage, IOG relays are still up and running and can be used. Cardano apps can therefore connect to both the stake pool relays or the IOG nodes. Where we are going is the peer-to-peer stage, in which community stake pools will connect only to each other's relays, and the IOG relays will gradually be turned off, as they wouldn't be required anymore. So the difference in the way they connect to each other's relays, the stake pools, is that it's not through a static topology file, but rather the nodes would be constantly detecting the best peers to connect to and maintain the network that way. So in that stage, Cardano apps would connect to only the stake pool relays, since the IOG relays would be turned off. Now we'll take a look at some graphs provided by IOG that illustrate the networking stages we just went through. So starting with the federated network. So we have IOG cores here that are producing the blocks. The cores each have their set of relays that are connected to each other so that the blocks are propagated to each core node. And then here we have the outer layer of the public IOG relays to which the apps, wallets, and exchanges connect to use the blockchain. Now we're moving on to the hybrid network, which is the current stage. In this stage, again, we have the core nodes, which are now not IOG core nodes, but instead community stake pool nodes that produce the blocks. They all have their set of or sets of relays, and the relays connect to each other between stake pools, and they also connect to the outer layer of IOG relays. So SPO relays can connect to IOG relays in order to sync the blockchain, and exchanges, apps, and users still can connect to IOG relays. Although in this diagram, every single exchange, user, or app, or whatever is connecting to an IOG relay. All of these connections go to an IOG relay. I think at this stage, this diagram should actually have like an app here that is connecting directly to an SPO relay, for example this one, because this is entirely possible at the current stage. So there is no need to connect exclusively to IO relays. Lastly, we have a peer-to-peer network graph, which is currently in development and will be the future stage. So here again, we have core nodes which are producing the blocks. They have their relays that are connected to each other. There is no outer layer of IOG relays that we saw on the two previous stages. So this means that apps such as this wallet, according to the legend, connect directly to SPO relays rather than the IO relays. Now we'll take a look at the peer-to-peer node components. So at the highest level, we have the peer-to-peer Cardano node, which has four main components relating to the peer-to-peer part of the node. These are the peer-to-peer governor, connection manager, server, and inbound protocol governor. Now, we mentioned before that server and inbound protocol governor could be grouped into one component. On the next slide, we'll explain why, but on this slide, we are looking at the responsibilities of each component, so we'll keep them separate for now. Starting with the peer-to-peer governor, its main responsibilities are requesting new connections, and in other words, peer selection, so selecting the best peers to connect to. Node-to-node mini protocols initiation on outbound connections. So this means that after a connection has been established, the peer-to-peer governor is the one responsible for actually starting the node mini protocols, such as transaction submission or syncing the blockchain from the other node. That's a peer-to-peer governor responsibility in the peer-to-peer mode. And it also keeps track of the peer count, so to try and keep the number of peers that we defined in the configuration of the node. The connection manager is a low-level component that takes care of connections. So it is aware of state transitions of connections, and it monitors each connection the node makes, both outbound and inbound. It takes care of low-level things such as TCP connections and negotiating the connection handshake. So when nodes talk to each other, when they start a connection, they first need to negotiate how exactly they will talk to each other. It keeps track of the total connection count, and it also is responsible for terminating connections when, for example, peer-to-peer governor asks the connection manager to terminate a connection. So in other words, connection manager is a low-level component that gets asked to do things relating to connections of the node by the other components. The server is a pretty simple component that basically is responsible for just accepting incoming connections and doing some dynamic rate limiting. And the inbound protocol governor is basically a component that does the same part of the node-to-node mini protocol initiations as the peer-to-peer governor does on outbound connections. The inbound protocol governor is the one responsible for starting and restarting the node-to-node mini protocols on inbound, both inbound and outbound duplex connections. So we'll take a look at what all those inbound, outbound, and duplex terms mean soon enough. Here is a diagram from the network specification document for Cardano node that illustrates how these components work together. So you might first notice that the inbound protocol governor and server are kind of grouped into one component. Actually, if you read the caption of this diagram, you will see that it mentions 3 components, so this is considered one component, but there is distinction between them because in the future they might become completely separate components. So that's why they're currently kind of grouped together, but they might be completely separated later on. Anyway, the server and the inbound protocol governor as one component, and the peer-to-peer governor as the other component share an instance of the connection manager component. So both of these components use the same connection manager. It is shared, and as we said, it takes care of the low-level stuff. So basically, peer-to-peer governor can request an outbound connection. It sends that request to the connection manager, and then connection manager is the one that actually does the connection going to, so this illustrates the rest of the network, basically other nodes. So the connection manager goes and actually attempts to do this connection requested by the peer-to-peer governor. The same thing happens if the peer-to-peer governor decides to unregister an outbound connection. So to terminate the connection, then again it passes this request to the connection manager, and connection manager as the low-level component takes care of that. On the inbound protocol governor or server component, the server component specifically is the one that accepts connections. So if a remote node sends a connection request to our node, the server component is the one that's going to accept this connection, and it's going to pass it on to, so this will be an inbound connection, and we'll pass it on to connection manager to do the handshake and so on. Inbound protocol governor has some methods that also get passed to the connection manager, such as promote to warm, demoted to call, and unregister the inbound connection. I think these methods will make sense a bit later, but for now it's enough to understand that peer-to-peer governor is in general in charge of the high-level stuff for outbound connections, and the inbound protocol governor and server are in charge of the high-level stuff for the inbound connections, and both of these components pass requests to the connection manager, which takes care of the low-level stuff of the actual connections. Now we'll start looking at peer types. So we already saw on the previous diagram some mentions of warm and cold. So these relate to peer types. There are three types of peers: cold peers, warm peers, and hot peers. Cold peers are simply known peers, so our node knows that this other node exists, but it's not connecting to it, it just knows it's out there. Warm peers are sort of an upgrade to that knowing that the node exists, where there is actually an established network connection to that known node. But it doesn't implement the main node-to-node mini protocols. So it's not actively syncing the chain from that node, it's not submitting transactions to that node, it's just simply connected to it. There is a connection. The purpose of warm peers is to basically serve as an immediate backup to peers that are active that might fail. So we need to replace an active peer with a warm peer. We already have the connection, and it's a good backup. But it also serves as optimization and adjustments, because like we said, the peer-to-peer governor is constantly assessing which peers are the best ones to connect to result in the best block propagation. So it might decide that a warm peer should be promoted to an active one in order to optimize the work of our node. So two main uses there. And then we have hot peers, which are basically what I was calling active peers. Just previously, hot peers are those with an established connection, like warm peers. But in addition to that, they use all the three main node-to-node mini protocols. So those are the chain sync protocol, the block fetch protocol, and the TX submission protocol. I think I maybe got some of the names wrong, but those are the three main node-to-node mini protocols, and it means that the connection is actively being used to sync the blocks and the transaction between the nodes. Now we'll take a look at peer groups, which is how the mentioned peer types can be grouped together, and we'll also look at transitions that peers can make between peer types and also peer groups. Here's a diagram from IOG that illustrates these peer groups. So we got three boxes, and starting with the largest one, the known peers group is the set of peers of all known peers. So any peer our node knows about, it's included in this group. Therefore, any peer type is included in this group. So all the cold, warm, and hot peers are part of the known peers group. A smaller subset of the known peers is the established peers group, which are peers that have an established bearer connection. And from our peer types, those would be only the warm and hot peers, while cold peers don't enter this group. And again, a smaller subset of the established peers is the active peers group, and those are peers that are actually running the consensus protocols. So out of our peer types, these are only our hot peers. Neither cold nor warm peers enter the active peers group. That's it for the overview of peer groups, and now on the right side we have some methods that indicate how peers can transition between peer types and peer groups. So let's go over that. We'll start off here at the top with this discover method. So how does our node even discover any peers? There are three ways. The first one is through our static configuration of the node. So any peer that we define in the topology file, obviously our node is going to be able to discover it just by reading its configuration. The second way is by using the ledger peers, that is the set of all the relays that have been registered on the chain. The way that selection works is that the node randomly selects peers from that set of all registered relays, but there is a favoring of relays of stake pools with higher proportions of stake. So if a stake pool has a lot of stake, its relays are more likely to be discovered by other peer-to-peer nodes. The third way of discovering peers is through gossiping, which is not implemented currently at the time of making this video, but it means that in the future Cardano nodes will be able to discover peers simply by talking to other nodes. So nodes will be able to tell each other about the nodes they know of. This will make it possible to discover peers that are not necessarily even registered on the chain. Now we'll take a look at this section of transitions between the known peers group and the established peers group. So promotion of cold peers to warm peers and demotion of warm peers to cold peers. So this is done to constantly refresh the established peers group with different peers. And the way it works is that about once per hour, the node is going to take 20% of randomly selected warm peers, and it's simply going to demote them and demote them to cold peers, and it's also going to take a randomly selected cold peers to promote to warm peers to replace those that have been just demoted. So that's the way the established peers group is constantly being refreshed with different peers. Now we're going to look at the section of transitions between the established peers and the active peers groups. Those include promoting warm peers to hot peers and demoting hot peers to warm peers. These promotions and demotions work very similar to the ones we just described earlier, but here the 20% of hot peers that get demoted are not randomly selected, but there is actually a ranking of hot peers constantly going on. So the 20% of the lowest ranking hot peers are the ones that are going to be demoted. And the ranking works in a way that hot peers are running the consensus protocols, right? So we actually sync blocks from hot peers. Our node is keeping track of which hot peers do we seem to get the blocks first from, right? So a hot peer that gives us new blocks before any other peers is a good peer, right? Conversely, the peers that seem to be the slowest in getting us new blocks are the ones that are going to be the lowest ranked, and therefore they are the ones that are going to be demoted and replaced with warm peers that are going to be promoted to hot. So this is the way the node constantly is attempting to always have the best possible connections for hot peers. And it's also why it makes sense to have the transitions between known peers and established peers. So the warm peers are constantly being refreshed, and with those refreshed warm peers, the hot peers are also being refreshed in order to build the best possible topology for the node. Now we'll look at the connection types. So some of these terms we already saw on previous slides. there are two main connection types, the outbound and the inbound connection. The outbound connection is one that our nodes initiates towards another node, so it's from our node, it's going out, it's outbound. And inbound is a connection that our node receives from another node, so it's inbound. Both of these connection types can be unidirectional or duplex. So both outbound and inbound can be unidirectional or duplex, where unidirectional means that the traffic on this connection is only going one way. So in the case of an outbound connection, an outbound unidirectional connection would mean that the connection is established with the other node, but only our node is using the node protocols towards the other node. While on duplex, it means the connection is being used in both ways. So the mini protocols are going both ways, from our node to the other node and from the other node towards our node. The same principle applies for the inbound connection, in which case the inbound unidirectional connection would mean that the other node is using the mini protocols, but our node is not towards the other node. And in the duplex connection, both nodes are using the connection to talk in node mini protocols. Now we'll take a look at connection states. First, for the outbound connection. So these states illustrate how a connection progresses from initiation to termination. So the outbound connection is first requested by the peer-to-peer governor towards the connection manager to initiate this connection. The connection manager then puts it in a reserved state, which is basically saying, okay, I'm gonna do this. Then the connection goes to an unnegotiated state, which means in the unnegotiated state, it means negotiation is currently taking place. So the nodes are talking to each other and agreeing on the protocol version they're going to use for the connection. And then we can progress to either an outbound state or a duplex state. We can go kind of both ways depending on the negotiation, right? But here basically we get to the point where the connection is going to get started. Well, the connection is already started, but the node-to-node mini protocols are going to get started. And based on the negotiation that took place, we're gonna know if it's a unidirectional connection or it's, in other words, our node is only using the connection for the mini protocols, or it's a duplex connection in which the other node is also using the mini protocols using the same connection. These are basically the active states of the connection, so it's actively being used. And then it may progress to an outbound idle state. So it means the idle state means that the node-to-node mini protocols are not running. If this happens, then this outbound idle state triggers a timeout that if the timeout expires, the connection is going to be terminated. So it first goes to the terminating state, and then the connection is finally terminated. So these are the main outbound connection states. The inbound connection states are pretty much the same, except there is one state missing here, and that is the reserved state. So because of the nature of inbound connections, right, the server accepts an inbound connection once it's registered, and it then progresses in the same way. So first it's accepted, then negotiation takes place, during which time the state is unnegotiated state, and then we have actually, so here there is an in-between idle state. So once negotiation is done, based on the negotiation, the data flow is going to be determined, whether it's unidirectional or duplex, and it's going to be in the idle state until the node protocols are detected from the other node to our node. So once our node detects that the other node is actively using the mini protocols, then we go to the inbound state of the data flow, which again can be unidirectional or duplex. So again, we have the possibility of a duplex state on inbound connections as well, as we mentioned, and it can be terminated the same way through the terminating state to terminate state the same way as the outbound connection does. So now I think we know everything we need to understand this diagram, which is also from the network specification document, and it illustrates the connection states and allowed transitions for both outbound and inbound connections. On this graph, the states are in boxes which are colored, and blue colored boxes signify outbound connections, green boxes signify inbound connections, and violet boxes signify duplex connections, which can be both inbound and outbound. So we'll try to go through all of this. It may seem a bit complicated at first, but once you get into it, it makes sense. So if we start from this starting point at the top, and let's say we'll look at the outbound connections first. So we request a connection, it goes to a reserved state. Once the connection is done, we are in an unnegotiated state outbound, which means negotiation is currently taking place. The result of that negotiation can be either a unidirectional connection, in which case we go down to this blue box and we are in outbound state unidirectional. We are using the mini protocols in one direction from our node to the other node. And this is basically the active connection. What can happen from there is if our connection stops using the node mini protocols, and that would mean that this demoted to called method is called, and it would put the connection in an outbound idle state with this timeout. I think this signifies a timeout. So if this timeout expires without the node protocols being restarted, then this commit unidirectional local method is going to be called and the connection is going to get terminated. On the other hand, if the result of the negotiation was a duplex connection, then we go into an outbound state duplex, again with this timeout. This timeout means that we are waiting, it's a timeout for the other node to start the mini protocols towards our node. If this does happen, then this dashed line, by the way, dashed lines on this diagram signify decisions, or let's call them decisions by the remote node, and full lines signify decision made by our local node. So okay, let's take a look at what happens if the timeout expires. Then we go into the outbound state duplex. So this is still a duplex connection, even though it's used only in one way. The result of the negotiation is duplex, but it's used only our node is using the mini protocols towards the other node. The other node did not start the mini protocols on time, timeout expired, and we are the only ones using this connection. On the other hand, if the other node does start mini protocols towards us, then this, so that is this dashed line that goes here, and this method is called promoted to warm duplex remote. Remote signifies at the end that this is a decision from the remote node. So the remote node promoted our node to warm, the mini protocol started, and then we enter the duplex state, which means that the connection is being used both ways in terms of a mini protocol. So our node is using the mini protocol towards the other node, and the remote node is using the mini protocols towards our node. From this duplex state, the remote node can again stop using the mini protocols, in which case we go back to the outbound state duplex with a timeout. So our node is still using the mini protocols, but the other one has demoted us to cold. It stopped using the mini protocols. So those are those two lines here on the left side are basically remote node decisions to and from this state, but we also have our local node decisions to and from this state. So if we are in a duplex state, we can demote to cold duplex local. So it means we demoted the remote node to cold. We stopped using mini protocols towards the other node, in which case we go to inbound state duplex. So it's a duplex connection that was negotiated, but it's an inbound state because it's only used by the other node towards us, and our mini protocols towards the other node have stopped. From this state, again, our node can start using the mini protocols, in which case promoted to warm duplex local is called, and we go back to the duplex state. So what we have left, we have from the outbound state duplex here, we can demote it to cold there. So this is a outbound state duplex. Only our node is using the mini protocols, although the connection that was negotiated is duplex. And if we stop using the mini protocols, then the connection goes to the outbound idle state with a timeout, and if the timeout expires, the connection is going to get terminated. Okay, so those are basically all the paths, I think, for the outbound connection. And then we also have the inbound connections. So in this case, we don't reserve the connection, we just accept it as it comes along. And we entered again the unnegotiated state of inbound. So in this case, inbound connection. Again, this can result in either a unidirectional connection, in which case we go to the inbound idle state unidirectional, where we wait for the other node to start the mini protocols towards our node, and if that does happen, then we enter the inbound state unidirectional, and that's it. That's the active connection for an inbound unidirectional state. The other node is using the mini protocols towards us, and that's it. So in the other case, if a duplex inbound connection is negotiated, then we enter the inbound idle state duplex, and we are waiting for there's a timeout here. We are waiting for the other node to start the mini protocols. So, and we also we have here awake duplex local, so our node starts the mini protocols as well, and this can go basically into either an outbound state duplex or an inbound state duplex. So our node or the other node starts using the mini protocols first, and then if both of them start the mini protocols, then we again end up in a real duplex state where both nodes are using the mini protocols. So that's it for this diagram. I think it's a bit hard to understand. I'm not sure I fully understand it, but it's good enough. We're now entering the last part of the presentation, which relates to node configuration files for peer-to-peer, and there are some settings we need to take care of. So in the configuration file of the node, the first one is test enable development network protocols. So as we said, peer-to-peer is still in development, so we need this flag to tell the node to even be allowed to use peer-to-peer networking. So it's a Boolean value. We got true or false. The default is false, so if it's not defined, it's going to be false. The second one is the enable peer-to-peer. Same thing, a Boolean value, and default is false. So we need to set both of these first two to true if we want to use peer-to-peer. Then we have the diffusion mode. So this is a string value that has two valid values, initiator only and initiator and responder. So this setting defines how our peer-to-peer node is going to work. Specifically in the initiator only mode, it's only going to request outbound connections and it's not going to accept any incoming connections from other nodes. While in the initiator and responder mode, it's gonna both ask peers to connect to them and accept and respond to connection attempts from other nodes. Important thing to say is that the default value is initiator and responder. So this mode supports the duplex data flow in both directions from two nodes, while initiator only does not support duplex. So even if we have an outgoing connection in this mode, it's never going to be duplex, right? So in initiator only our node is going to run the mini protocols in the direction of the other node, meaning it will pull blocks from the other node, but the other node will not pull blocks from our node. So for a relay, for a stake pool relay, it makes no sense to run initiator only, right? Because you will never advertise your blocks in this mode, which you definitely want to do. So the default value, initiator and responder for duplex connections, and the last four are integer values relating to the targeted number of peers of different peer groups. So we have the target number of active peers, of established peers, and of known peers, and also of root peers. So active, established, and known peers we already went through earlier in the presentation, and root peers we're just going to get into on the next slide, which relates to the node topology file. And just before that, we'll have a look at the peer-to-peer tracers that were added for the peer-to-peer mode. So these settings control what ends up in our Cardano node log files. I listed some of the ones that I think are most important, but this is not a full list. So if you're interested in a full list, you can go to this link on the Cardano node GitHub, and I'll put the link in the description. So we got tracers relating to connection manager. Most importantly, the counters is going to give us the count of every connection type. Then we have some tracers relating to the inbound governor, so logs around inbound connections. We have trace ledger peers, so relating to the relays registered on chain for peer selection, and then we do have the peer selection tracer and the peer selection actions, as well as the counters. Usually the counters are kind of the most important for us because they give us a high level, overview of everything. So if we see, the count of our peer types, the count of our different connection types, we have a good idea of what's going on. And the trace server, so relating to the server component of the peer-to-peer node. Most of these are true by default, the ones that I've listed. So out of these that I've listed, only the trace ledger peers and the trace server are false by default. So if you want to see those logs, you'll have to turn those tracers on manually. The last thing we need to look at is the node topology file, which for the peer-to-peer version of the node has considerable differences to the static file you may be used to. So let's look at that. So here we have the static topology file that you may be used to, in which we simply define a list of peers that our node will connect to with address, port, and valency combinations. While in the peer-to-peer topology file, we have it's a bit more complex, and we have three main settings: the local roots, the public roots, and the use ledger after slot. So the local roots are basically your bootstrapping nodes. You can define many different groups. So groups is an array. What local roots are basically, as I said, bootstrapping nodes, and these are the nodes that your peer-to-peer governor is always going to try to maintain a hot connection to. So any peer defined here is going to be attempted to be used as a hot peer at all times. Well, depending on how you set the valency, it will I think respect the valency. So if you have 10 peers defined, but you only want to connect to 5 of those 10 at a time, you can do this. The advertise false is I'm not really sure what it is, but I'm pretty sure, my best guess is that this is for the gossiping feature of the nodes, which is not implemented, so there is no gossiping. In other words, the nodes can only discover relays that are registered on chain by stake pools rather than gossip between each other and find out what other nodes is the other node connected to that might be a good node for our local node to connect to as well. So gossiping is not yet implemented, and I guess the advertise flag means, do you want to tell other nodes about these nodes or not? So for example, you would definitely, for a relay node, you would definitely want to have your block producer here, and in which case you definitely wouldn't want to advertise that node to other nodes. You want to keep it hidden and only known to your relay nodes. Then you have the public roots, which is basically a backup for local roots. So if some of the local roots connections fails, you have public roots as backup that the node can use to bootstrap on startup. And then the final setting is use ledger after slot. This is and also if the use ledger after slot, okay, first the use ledger after slot means that use the ledger, use the registered relays that are registered on chain, detect them and connect to them as you see best fit after certain slot. So use the state after a certain slot. And if this for any reason fails, then public roots is also a fallback to that. So local roots always keep a connection if it's possible. Always keep the connection to local roots. Public roots more as a backup to both local roots or the registered relays on chain if it fails for any reason. The previous slide showed what would be a normal relay peer-to-peer topology file. So in this slide we'll look at the block producer topology file for the peer-to-peer node. So in the static topology of a block producer, you would have your relay defined, in this case only one relay. And if we want to switch that to the peer-to-peer topology, then this would mean that we define our relay as our local root, right? So we can put multiple relays here, of course, but in this example there is only one. And the public roots config is it still has to be defined because the node requires it to run, but we leave the access points empty, right? So we don't define any public roots. The block producer should not have any public roots. It should only have the local root for our relay or relays. And besides not defining any public roots, we also disable the use ledger after slot setting by setting it to -1. So we don't want this node to discover really any peers from the ledger. We just want it to connect to our relay, and that's it. And that's the end of the presentation. So now we'll go test this peer-to-peer feature on the Cardano testnet. I'm in the server now where I set up a Cardano node connected to the public testnet. I use the guild docs for setting up the Cardano node. The link is going to be in the description. If you need help with that, the docs are pretty straightforward, but there's also some older videos on this channel about setting up nodes, also following this documentation. So if you need help with that, you can check that out. And now just to show you what kind of setup we have here. So it's pretty much default. The two important files are the config.json, which is the node configuration file. So you see there is no reference to peer-to-peer. It's running in the normal static topology file mode. And the topology file is the default that we get with the guilddocs setup, and the relays in the topology are just the Cardano testnet IOHK relays. So if we check guild live view, we can see the status of the node. It's on epoch 223, which is currently the latest epoch, so it's on tip of the chain, and it's running in the normal mode as a relay on testnet, and it has two outgoing peers defined in our topology file. Peer-to-peer is disabled. So this is the default that you would have when you set up a node. And now we're going to convert this node into a peer-to-peer node. So we're going to edit the config file, we're going to edit the topology file, and start it up in the peer-to-peer mode. So let's go back to that files folder. And so first let's edit the config.json, and let's add the settings we talked about. So I'm just gonna copy them over because I have them ready on the other screen. Then we'll see them. Okay, so the first one, as we said, test enable development network protocols is true. To be able to set this enable peer-to-peer to true as well. Diffusion mode, we're going to be initiator and responder, so we're going to allow duplex connection. Target number of active peers, this we're going to set to 20. So this is the same as when you're using the static topology file, you would set the number of peers to be around 20. IOG recommends not more than 20, I think, because it starts to be a lot of load for the node to handle so many connections. So I'm gonna set this to 20 as it's considered sort of a best practice. Target number of established peers. Yeah, actually we can check for all these three groups: active peers, established peers, and known peers. We actually do have some indication of what are good values for these settings. So we got active peers 2 to 20, right? So below 20, we'll just set it to 20 for now. We could set it to a bit less. Established peers, so the ones that have a connection to, expect 10 to 50. So we set that to 50, I think. Yeah, that's fine. And known peers, so all the known peers that the node knows about, we expect 1000. So I put 1000 in here as well. And the last one is root peers, which is 100, but I guess this setting, for this setting, it's only important that the number you put in here is equal or greater than your actual number of root peers in your topology file. So if you want to connect to, for example, your BP and two other relays, then you need at least the target number to be 3. I think if you put more, it doesn't have any negative effect. So I think like we can leave this at 100. It's just to make sure that all root peers, there's space for them to be connected to. Okay, that's it for the config file. So next up is the topology file. The default topology file that the node is using right now, we already saw. So instead of editing it here, I prepared a peer-to-peer topology file that we can just take a look at. So it is the template we saw in the presentation. It's exactly the same. The only difference is that here, so in my setup for this video, this is going to be the IP address of the producer that I'm using on testnet with the port, and that's going to be my only local route. So I always want to keep my connection to the to my BP, and valency is 1. And I defined public routes as some backup relays to bootstrap the node in case something goes wrong. So I just left the Cardano IOHK testnet. Oh, sorry. Here I put mainnet. So that needs to be testnet since we are on testnet, and okay, that should work. So the use ledger after slot, I just put in 0. I think that's gonna be fine. Yeah, that's the topology file. So now we edited both files. The node should be ready to run in peer-to-peer mode. So all that's left to do is to restart it with the updated files. One more thing, so the topology file peer-to-peer, I need to replace the topology file with this one. So when I restart the node, it's going to use the new topology. Restart C node. Okay. And that's it. Now it needs to start up, and we're going to check Guild Live View in a sec. Here's our Guild Live View of the peer-to-peer node. So you can see this connections tab looks a bit different. We got peer-to-peer enabled now, and we basically have 3 columns for the peer-to-peer mode to explain what's going on. So on the left side, we got incoming and outgoing connections. In this case, we got 1 and 44. So this relay is not yet registered on the chain. So obviously other nodes cannot discover it. Hence we have only outgoing connections. And the 1 incoming connection is just from the block producer that knows about this relay. In the middle section, we got the peer counts: cold peer, warm peers, and hot peers. We can see that hot peers never goes above 20, as that's what we defined in the topology, in the node config file, as the target number of active peers. And on the right side, we got the nature of the connections. These can be unidirectional, bidirectional, or duplex. The duplex connections means that our node initiated the connection towards the other node, and the other node also initiated the connection to our node. So that's a duplex connection showing in a GLive view. The bidirectional connections are ones that both nodes can use to run the mini protocols, but the result of the negotiation was a bidirectional connection, but it's not necessary that they are actually running the protocols. So bidirectional means both nodes could use the connection to run the protocols both ways. And unidirectional is a unidirectional connection, either outgoing or incoming. So the thing I wanted to illustrate in this video is the effect of registering the relay on the chain. So I'm going to register the relay on the chain, and then we'll check Guild Live View again to see the effect on hopefully other nodes discovering this node and seeing more incoming connections to our node. So I just updated the testnet pool that I'm using. So there's an update here 2 minutes ago in epoch 223. I'm not sure if Cardano scan is going to show us the... Yeah, so I registered the relay, and okay, so I'm gonna keep track of the Guild Live View, and we'll see how long it takes for other nodes to discover ours now that it's registered on chain. All right, so it's been a while since the relay has been registered. And if we look at the Guild Live View again, we'll see we're still in epoch 223, but it's been a couple of days since I registered it. And now we see the incoming connections count has increased. So this shows that other nodes are requesting connections to this relay node, resulting in incoming connections being recognized by our node. So once the peer-to-peer relay is registered on chain, that's really when it gets discovered. And looking at this Guild Live View, this connections tab, I can definitely say that this relay is now well connected to the network, right? It has, first of all, like we mentioned, more than 4 hot peers and more than 4 bidirectional connections. That's a good indicator right off the bat. But we also see that we actually have incoming connections. So that means other nodes are aware of our node as well, and that's a good sign. So a day or two after being registered on the testnet, already nodes start to discover this relay on their own. The last thing I want to show you in this video relates to the tracers that we took a look at in the presentation. So we've been looking at Guild Live View to sort of analyze our peer-to-peer node, and Guild Live View uses these metrics from the tracers behind the scenes. So now we're just going to have a quick manual look at them. So we can get all the node metrics from the node's Prometheus port, which is 12798 by default, and the endpoint is metrics. So querying this on localhost would export all the node metrics that we have enabled. This can then be exported to Grafana for monitoring, etc. If you want to do that, there's a video on this channel about setting up a Grafana monitoring for your node. So that setup can be extended with these peer-to-peer metrics as well. So these are all of the node metrics, and now we're just gonna grep for the ones relating to peer-to-peer. So we can grep for connection manager, and it will give us the connection counts of connections of different types, right? So outgoing, incoming, duplex connections, unidirectional connections. We also have prunable connections. Now those are, as far as I understand, basically connections that can be dropped if the node requires more space for other connections. They can be dropped because of basically the outgoing and incoming, the way outgoing and incoming connections work. So the duplex flow can be maintained on just one connection instead of both. So I think one of them can be dropped, something like that. That's the connection manager. We can also look for inbound governor. So this would, in this case, we get peer types for the inbound governor. So we got cold peers, warm peers, hot peers, also the idle peers, which are, if you remember, the ones that we are sort of waiting on from the other node. We also have the what's left, like the peer counts. So we got peer selection, we got 20 hot peers, 29 warm peers, 52 cold peers. So these are some of the tracers that we mentioned in the presentation, and this is how you can get to them when running the node.